Hello, my name is Zhang Jialu, and I'm delighted to introduce our work at ICCV 2023 titled Neural Characteristic Function Learning for Conditional Image Generation. Existing conditional GANs applies a conventional GAN structure to optimize adversarial training can be categorized into two parts based on conditionally Px given y and Py given x. The former directly concatenate data and auxiliary information, which can lead to information aggregation mismatches. The latter predicts Py given x through classifiers, but they rely on cross-entropy loss, which suffers from incomplete comparisons between well-separated distributions. These problems can lead to instability and mode collapse during training due to the ear-pulse discrepancy measures between distributions. IPM GANs, like Weierstrass GAN, Fisher GAN, MMD GAN, and characteristic function-related GANs, have effectively used integral probability metrics for unconditional generation. This reformulates cross-entropy loss into a more theoretically complete distance metric. While IPM has shown promise in stabilizing C-GAN training, its integration into C-GANs only started recently, slowing down advancements in this area. To overcome these challenges, we introduce a novel approach, the Conditional Characteristic Function GAN, or CCF GAN. CCF GAN leverages the IPM to enhance the performance of C-GANs. Our proposed method makes three significant contributions. First, we developed neural networks to upper bound the CF discrepancy, which we refer to as the neural CF metric. Second, we established CCF GAN by explicitly modeling conditional distribution. Finally, we propose a conditional CF loss function based on the neural CF metric for joint distributions. We prove in our paper that the upper bound L against D is a valid distance metric for measuring distributions. We demonstrate in Figure 1 that without any discriminator modules, optimizing a generated network solely by setting T to be the standard Gaussian distribution can generate realistic images of meanest digits. The CF definition allows for an explicit decomposition of Px and Py given x, as shown in equation 4, when employing the NCF network F to calculate Tx. The CF definition becomes equation 5. Besides, we sample Ty according to fixed rules and apply a classifier to predict Py given x. By substituting the new joint CF into the NCF metric, we arrive at the final loss function for training CCF GAN in equation 6. This approach enables the effective learning of data distribution and auxiliary information with different importance, allowing for optimized discrepancy measurement between real and generated joint distributions. We also demonstrate in Figure 3 that CCF GAN can well separate real and generated samples at the middle stage and align them at the end stage. To evaluate CCF GAN performance, we first conduct experiment on synthetic dataset. Our CCF GAN almost recovers the ground truth distribution, whereas others are either overconcentrated or imbalanced. This validates the effectiveness of employing the NCF in our CCF GAN, which stably and accurately measured two distributions even when they were supported in low dimensions. In contrast, existing C-GANs that are designed based on the cross-entropy loss may suffer from the ear-pulse discrepancy measure, such that the fitted distributions were biased. Additionally, we extended our evaluation to realistic datasets. CCF GAN achieved outstanding FID and IIs on quantitative results, particularly on the challenging ImageNet dataset. Figure 5 showcases conditional image generation on CIFAR, VGG Phase 2, and ImageNet, while smooth interpolation demonstrates the desirable continuity of the latent space learned by our CCF GAN. Additionally, we assessed stability through repeated training under various conditions. As shown in Figure 6, CCF GAN consistently outperformed other models, demonstrating its robustness. Moreover, ablation studies show CCF GAN performs well under Ty from different distributions, which further validates the stability and exceptional performance of CCF GAN. Thank you for your listening.